Okay, so we have looked at tables quite a bit for the exponential functions, and when we're looking for exponentials, we're looking for a number that we could multiply by that would give us the next number in the list, right? So if I look at example 1, it asks me for each one of these to find the growth factor. So in this case, what could I multiply by that would give me the next number here? Almost 1 1/4. It'll be 1.2, 1 1/5. There. So if I multiply by 1.2, that'll give me 120. And then if I multiply by 1.2 again, we could check, and this will be, if I give you something like this, will be calculator active. You can check, and you'll get that same thing again, and so on, right? So my growth factor, which typically we use a B for here, or it depends on whether they're giving you a sequence or a function. In this case, they've used the f of x, so we're going to assume they're using the function. We'll call it B is 1.2, like in the y equals a times b to the x equation. This would be our b value. If they were using sequence notation, we would call it r for our common ratio, right? So, what about the second one? I'm going to pull up my calculator while. If we're just looking from 2 to 10, what can you multiply 2 by that would give you 10? 5, right? So, but then 10 times 5, obviously, is not 34. So this one's going to be weird, right? On number 1, let's say you didn't really come up with the 1.2 very well. You could have done 120 divided by 100, and that would have gave you the 1.2. Or any of the terms. You could do 172.8 divided by 144, and that would give you 1.2. If you take any term on number 1 and divide it by the term before, it's going to give you 1.2 because that's what you're multiplying by. But that is not happening here, right? Because if I do 10 divided by 2, it gives me 5. If I do 34 divided by 10, it gives me 3.4. So it's not working here. However, I am going to tell you, this is exponential. So let's look at it how we do if we're looking at arithmetic sequences. So this, from 2 to 10, that goes up by 8, right? We just went up 8. And then from 10 to 34, we went up by how many? 24. And then from 34 to 106, what is it? 72. And then from 106 to 322, 216. Now, those numbers are multiplied by 3, right? So 8 times 3 is 24, times 3 is 72, times 3 is 216. So while I'm not seeing in the original function problems, I'm not seeing the increase where I can multiply. I do see it when I look at my differences, right? So what is happening if you see this here, where these numbers cannot be multiplied by a number, but the differences could, is that you have an exponential function that has been shifted up or down. Okay? So, if I were to take, let's see, what would I need to take away? Well, that gives you a 0. Add 2. Yeah. If I add 2 to each one of these, that gives me 4. Add 2 here, I get 12. Add 2 here, I get 36. Add 2 here, I get 108. Add 2 here, I'd get 324. Right? So if I added 2 to all of these, then if I look at 4 times 3, I'd get 12. And then times 3, I'd get 36, 108, 324. Right? So what's happening here is my equation is going to look, let's see. I pulled this from his notes and it made sense when I looked at it. So we have to add 2 for it to work, right? If we add 2, we get 4, 12, 16, 36, 108. So that would be 4 times 3 to the x power minus 2, I think. Let's see if that works. 4 times 3 to the, let's put second, minus 2. That gives me the 34 that I had. So like here I had to add 2 to get numbers that would work. But when I write this equation, I'm not using 4, 12, 36, 108, 324. I'm going backwards, so I had to subtract the 2 in the equation. One thing you can always do if you're trying to write, you might be asked to write an equation. This one actually doesn't ask you to write the equation. It only asks for the growth factor. The growth factor is just b equals 3, right? So if you're asked for the growth factor, you don't have to think so much about what number would have to be added here, but just rather what you're multiplying your differences by, right? But if they do ask for the equation, one way that you can always check is when you get your equation, plug the numbers in, right? 4 times 3 to the 0 power minus 2 gives me 2, which is what I'm supposed to get on the table. And then I could go back and plug in 1 and see what I get. And I get 10, which is what I have on the table. So these are a little bit tough to think about sometimes. What is really important is that you're able to recognize that even though there's not a number I can multiply by here, like on number 1, it's still exponential growth, and then it's been shifted up or down for that. Okay? 3, we're going to have a similar problem, because 7 to 13, like if I do 13 divided by 7, I'm going to get a decimal here, 1857. But if I do 13 times that number, I am not going to get the next term, right? And so it's not looking very exponential as it is, but I am seeing a characteristic of exponential that you'll see is that you start off growing slowly and then grow faster over time. So whenever you suspect something might be exponential, but you can't find a growth factor for it, look at the differences. So from 7 to 13 is up 6. And from 13 to 25 would be 12. And then from 25 to 49, 24. And from 49 to 97, 48. That is multiplying by 2. So my value would be 2 there. Now, if they ask us to write an equation for f of x, I know I'm going to have some number times 2 to the x power, but and then something is going to be added or subtracted over here on the end. So for this, if I just subtracted 1, that'd give me 6, right? And if I subtracted 1 here, it would give me 12. And if I subtracted 1, it would give me 24. Subtracted 1, that'd give me 48, right? Subtract 1, that'd give me 96, right? Those numbers would be, I would have 6 times 2 to the x power. What would I put on the end? Plus 1. instead of minus 1 because we're doing sort of the opposite. And whenever you get your equation, check your answers. Do 6 times 2 to the 0 plus 1. Make sure that you get what is in the table there. And that's what we've got. And then we can plug in 1 and 2. You probably want to check a few. You also, here's another option for that on the calculator. You can put your equation in y1. So 6 times 2 to the x power plus 1. And if we go to the table, we can see all those values at once. So if we go to the table, why is my table not working like I want it to? It's in ask mode. So if I go to second window and I'm going to start at 0, we'll change this back down to auto. And now I go back to the table. 0 is 7, 1 is 13, 2 is 25, 3 is 49, 4 is 97. That's correct. Okay, so we can have exponential functions that are not easy to find the growth factor on. Is the main thing that we're pulling away from this. I'm not sure why they chose to put this in. I guess it's because of the data modeling part of this. So if you were seeing these patterns in a graph, you would know that you need to do exponential regression, but it would have to have that plus or minus on the end, which we can't do very well with calculator. So I think they would only ask you like a problem like this for it. Okay, let's look at the next slide here. All right, so whenever we are modeling exponential functions from data, we do not have to have a lot of information to write an exponential equation for a situation. One way that we can do it is if they give us the common ratio in the initial value, that is enough to write the equation. Another option is that they give us 2 input-output pairs and tell us that it's exponential. So the model can be constructed by hand or using technology. And we need to be able to do both. All of these we are going to use our calculator later on. I'm going to show you both how to do it using an exponential regression and how to just do it by hand. A lot of times I think it's easier on a lot of these just to do them by hand than rather than do the regression, although you may prefer the regression. This sort of stuff generally has to be given to you on a calculator active section because the numbers are going to be hard to deal with, so you have the option of doing either one. So in this case, we got the population of a small town was 4,325 in the year 2010. The population of that town is growing at a rate of 1.2% per year. Write an equation that models the population of the town X years after 2010. Okay, so for this equation, we kind of got to think about what information we're given. We are given the population of a town at a certain time, right? And then we're also given the growth rate for the town. So this is the scenario where we have basically a common ratio and an initial value for this. So when we write the equation for this, you can use, I'm going to call it P of X for population. You could call it Y equals. You could use any letter over there instead of P if you wanted here. And the initial population is 4,325 people. And then I need to multiply this by my growth factor and raise it to the X power, which will be my time. Okay, what number should go here for my growth factor? Close. It's part of it, 0.012. However, okay, if we use what Lucas said, which is just changing this to a decimal, right? If I type that into the calculator, 4,325 times 0.012 to the X power, and I go to the table, my population goes from 4,325 to 51.9 to 0.6228 Is that growing? It is not. But if we do like Granger said, and we add in the 1 right there. If I go back over here to my y equals, and I add in the 1 right there, and go back over to the table, now I've got 4,325, 4,376, 4,429. We have growth now, right? So whenever you're finding this B value right here, it is going, for growth, it is going to be 1 plus your rate as a decimal. Okay, that's whenever you have growth. Right, because you are keeping 100% of the people that are already there, and you're adding 1.2%. Right. Now, I don't know if I've got one for this, so let's just write it down. What about if you have decay? What if your population is declining? What would we do for the B? We'll do 1 minus the rate as a decimal. So, like, for example, in this case, if it was decay, I'd do 1 minus 0.012, which would give me like 0.988, I think, for that. A lot of times I'll tell students to think about this not as the percent that's decreasing, but the percent that remains, right? So if your population was decreasing by 1.2%, 98.8% would still be staying there, right? So these can be written by hand. In my opinion, it is just easiest. Well, and actually, when you got this rate, you really just have to do this by hand right here. So let's go over to the next problem. All right, so for 0 less than or equal to t less than or equal to 30 minutes, the number of fans inside a large sports stadium can be modeled by the exponential function f of t equals a times b to the t power, where f represents the number of fans inside the stadium t minutes after the doors open. All that is telling you is that this is exponential, right? It's a lot of words to tell you it's an exponential situation. It's not linear, it's exponential. There are 47 people in the stadium 2 minutes after the doors open. There are 2,602 fans inside the stadium 20 minutes after the doors open. Find the values of A and B for f of t. All right. So for this, you have a couple different options of what you can do. The first is how you can do it by hand. The second is how you will do it with the calculator. So let's look at this by hand. For this, so I know like that if I plug in 2, I will get 2,602. So that's telling me like, f of 2 is 47. 47. I'm looking at the wrong number there. F of 2 is 47. So if I think about this equation right here, that means if I plug in 2 for my t, right? So if I've got a times b squared, I will get 47. Now, that has 2 variables, so I can't really do a lot with that. I also know that f of 20 is going to be 2,602. Right? So if I plug in 20, so I've got a times b to the 20th power, I will get 2,602. about this for a second. All right, so make sure I'm doing it right before I continue. All right, so in this case, since both of those equations have two variables, you can't really solve them by themselves. But what we're going to use here is a form of substitution. So for substitution, I solve one equation for a variable, and then I can plug it into the other equation. Which equation would be easier, which variable would be easier to solve for, your A or your B? It's going to be A because it doesn't have an exponent, right? So you can use either equation. That top one looks a little bit more simple, so I'm going to take 47 equals A times B squared. I'm going to divide both sides by B squared. Okay? So that tells me that A is going to equal 47 over B squared. So if A equals 47 over B squared, I can take this and I can plug it in over here. Okay, so that'll be 2,602 equals 47 over B squared times B to the 20th power. Now, that B to the 20th power is not a fraction, so I'm going to make it a fraction by putting it over 1. And what is going to happen with my B's right here, where I've got some on top and some on bottom? Perfect. So I'm going to cancel those two B's on the bottom with two of the B's that are on top. And so now I've got 2,602 equals 47 B to the 18th power. Okay, this is, I mean, the numbers are kind of high, but we just got one variable now. And what would I need to do first to solve this for B? Divide by 47, definitely. All right, so let's use our calculator. All right, so we've got over here 55.3617, and so on. Keep that number in your calculator. Is going to be B to the 18th. All right, what have we got to do last? Root it by 18, 18th root, right? So, let's look at how to do that. Yesterday, we learned, now this is how I usually do it in the calculator. There's two ways though, so I'll show you both. Yesterday, we learned about how roots could be fractional exponents, right? So, the 18th root of 55.3617 could be written like this. 55.3617, and so on. Keep that number in your calculator. Raised to your exponent on the inside would be a 1, on the outside would be an 18. So it would be 1 over 18th power. And we can do that in the calculator. We're just going to take this number right here, raise it to the 1 over 18 power. And we get that B equals 1.24981, and so on. Okay. And we're not done. Because what do we got to find the values. We found B. What else have we got to find? A. Now, let me do back up and show you. If I like to just do fractional exponents because it's no special button. Plus, it reminds you about fractional exponents. But you can do an 18th root. If you go to the math menu, number 5 has an X and then a square root. Here's one reason I don't like it. If you just do it like this, it's going to use that answer right there. So what you have to do first is you have to do 18. Then you have to go over here, do number 5. It'll do 18th root. Go up here and get this number. And there it is. So you can do a root on the calculator also. That works as well. All right, how do you guys think we're going to find A? Plug it in for B in either one of our original equations, right? I would use the top one because it's a little bit easier. So 47 equals A times 1.24981. Keep that number in your calculator. Squared. So if I square this number, I've got 47 equals A times 1.562032. And then I'm going to divide by that number. So if I do 47 divided by that number right there, I'm going to get 30.089 for my A. So there's my A, there's my B. Yeah, it'd probably take a while. Yeah. I don't know. To get to 3 decimal places, it'd probably take you forever. To get close, maybe not. Yeah, you'd have to. It'd take forever. All right, so this is an option. I will say this is a little bit easier to do if instead of giving you the stadium at 2 minutes, they give you the stadium at 0 minutes. If there are 47 people at 0 minutes, then A is 47, right? And you don't have to find A. It makes it easier to find B if you do that. It's still the same idea, but it does make it easier to do if you don't have this at 2. So this is kind of lengthy. There is another option, so let's look at what that is. Okay. All you have to be able to do a linear regression is 2 points. So here is another option. This is doing for that same thing. We can go to Stat. Go to Edit. We're going to clear out anything that's already there. So Stat, Edit, and we are going to enter our points. At 2 minutes, we had 47. Oh, wait, wrong thing. 2 minutes, we had 47 people, and then at 20, we had 2,602. This is just showing you how to do what we just did on the calculator. So we're still on example 5 as far as doing this. So if we want to do an exponential regression, we are going to go to Stat. We're going to go over to Calc. And just like we've done with all those other regressions, we're just going to go down here. This time we want to pick EXP reg. That's our exponential regression. That's 0. There, we'll hit Enter. It should say L1, L2. We usually like to store that regression equation. They didn't ask us any other questions, so it's not all that important to do it here, but we usually like to. What do I have to hit to get Y1? Alpha trace. So alpha trace, Y1, and then we're going to tell it to calculate. And there are those same numbers that we found long ways. Right? I have a feeling that you guys may possibly prefer the second method right here, which is why I did the first one first, or you may not even listen to me. You'd be like, why are you doing this, Miss Hyatt? It's not that bad. All right, try 6. All right, 6 is asking you, it tells you that that is exponential, and it's asking you to write that equation. So try 6. And you can do it by hand if you would like. See, I didn't leave much room there. Kind of expecting you to do it with the calculator this time. I need to look through all of the practice questions that are on AP Classroom. I don't think so, because it is really hard to do without a calculator because the numbers get crazy. I need to look and see, and if there is, I'll try to give you guys one where you can see that. A lot of, like, if they give you numbers small enough for you to be able to do it without a calculator, you could probably just guess the pattern easier than you can solve it. So I think it's probably going to be calculator active. All right, is everybody still see some buttons? Push. Check with your neighbor, see if you got it. See if they're getting the same as you. Alright, here's what I have. Is that what everybody else is getting? Notice, like right here, on the AP exam, you're going to be required to round to at least 3 decimal places. Or you're not required to round to 3 decimal places. You must be correct to 3 decimal places. So, for whatever reason, I kept 4 decimal places on this first one. I could have stopped right here at 801. That would have been fine and not that difficult. If you want to round this one to 3 decimal places, you got a long string of 9s, right? So, like, this 9 rounds that 9 up to a 10, which rounds that up to a 7. So you would really just get 0.700 if you rounded it up. I don't like doing that because I always second guess myself if I'm doing it correctly. It's okay to keep extra decimal places, so just do that. So I just kept all the 9s till it didn't matter anymore and cut it off there. Or keep the whole decimal if you want. That's fine for that. All right, let's keep going. All right, now, sometimes we do not use the A times B to the X formula. Instead, we might use the formula that we use for continuous growth or decay, which is Y equals PE to the RT. Have you guys seen E before? You have. So I think whenever you do, there's some exponential stuff in Math 3. And I think whenever you do that in Math 3, that's where that should be introduced. E is just a number. If you go back over here to your calculator, I put here that E is approximately 2.718. You don't want to use that rounded version, though. There, it is stored in your calculator. If you do second in the division key, that's your E right there. You can see it's 2.718281828. It's actually not repeating. It looks like it repeats there, but it's not. It goes sort of crazy after that. It's called Euler's constant. Euler is spelled with a E, even though it doesn't look like it should be spelled with an E. It's not English. We may look a little bit later about exactly where that comes from. But E is used a lot for continuous growth, right? So you could put your money in an account and it could grow, you know, yearly, or it could grow monthly, or it could grow daily. If your money is growing continuously, E is what you would use here. So for these problems, they will tell you that it is going to be using this formula here. Because otherwise, if they just say it's exponential and they don't say anything about continuous growth or the E to the RT formula, just use A times B to the X. So you'll probably see this formula somewhere in the problem if you're expected to use this formula. You could use either one to model growth. What has sort of been found in research is if you use E for a lot of real-world cases, it may be more accurate. So a bacteria culture begins with 17 bacterium and grows at a rate of 31% per hour. The bacteria growth can be modeled using a function in the form of y equals PE to the RT. Write the equation for this situation. So in this formula, P is your principal. It's used a lot for finance. That's why it's got the P there. It's just your starting value, right? For bacteria, in this case, that's going to be 17. And then R is your rate as a decimal. It does not have the 1 added to it or subtracted from it. So it would just be your rate. And then T is some sort of time. It depends what kind of time that is, depends on what your rate is increasing by, the time period for that. This is 31% per hour. So time is going to be measured in hours for this problem. If it was 31% per year, time would be measured in years for this one. So for our equation, we're going to have y equals our principal, our starting amount is 17. E is a number, it does not get replaced. And then we would raise it to the RT. So the rate, 31, would be 0.31. Again, you do not add 1 to it like you do on the A times B to the X problems. And then we'd multiply that by T. And then we should say over here, T is hours. And then it asks how many bacteria will be in the culture after 6 hours. What have we got to do to find that? Just plug in 6 for T. So if we go over here on our calculator, 17. E, again, is the blue button and your division key. Or you can do the blue button and natural log, and it'll do E and raise it to a power. Either one is fine there. 0.31 times 6. 109.203. Actually 204 if we round that to 3 decimal places. What I would do for this on like an AP exam, I'd say 109.204. I've got it rounded to 3 decimal places. And then I would say 109 bacteria. I had that. That should be bacteria. Is 1. I only have 1. I would go, you can't have part of a bacteria, so I would go with that as my final answer. But I'd write this number down too, just in case they were looking for the decimal place there. Everybody good there? All right. Let's see. We're going to run out of time. Let's do, okay, we need to do 8. If we run out of time for that last one, we'll be okay. Actually, there's a couple more things. But, all right. After 50 deer were introduced to a large wooded area, the population of deer in the wooded area can be modeled by the function d of t equals a times b to the t, where t represents the number of years since the deer were first introduced to the wooded area. The population of deer increases by 13% each year. That first part is just telling you this is exponential, we need to write the equation first. So d of t is going to equal, what's my starting amount of deer? 50. And then what should I use for my b value? it comes from 13%. It's going to be 1.13 because 13% as a decimal is 0.13, and we're adding 1 to it, so it'll be growth. And then that'll be raised to the t, where t is years. All right, then it wants to know what's the population of the deer after 6 years. What have we got to do there? Just plug it on in. So 50 times 1.13 to the 6th power is going to give us 104.098. Which would be 140. Okay, now, C is not asking, it is asking us to plug a number in, but we're not plugging in for T, right? For this one, we're plugging in over here for like our Y value, right? We want to know when Y hits 5,000. So we got 50 times 1.13 to the T power. In Math 3, you should have learned how to solve that by hand, probably. But you got to use logs, and we haven't been over logs again in this class. So right now, let's just use the calculator to solve it, okay? What I'm going to do is I'm going to go to, this is like the Coach Wood method of solving equations, right? It's just he usually likes to use Desmos instead. You can just type in your equation, 50 times 1.13 to the x power. Let's use an x instead of a t just because it works better on the calculator. And then in the second line, I want to know when this equals 5,000, so I'm going to put 5,000 right there. Now, probably if I graph this, it's not going to be very helpful. Why is nothing showing up? Way too zoomed in because I need to go all the way up to 5,000 on my y's, right? Really above 5,000. So let's go to Window, and I'm gonna start. I'm not gonna change anything else just yet, but I'm gonna make that Y max. It needs to be more than 5,000. If it's exactly 5,000, the line will be at the very top of the graph, and you won't be able to see it. So let's go like 6,000. And let's hit graph and see what it does. I don't know if it'll be very good. Yes. So like, I can see this is increasing, but it barely has increased here, right? What would I change so that I can see more of this side of the graph? Because this is going to go up, but it's like way over here. X max. So if I go over here to my window and I change my X max, I'm going to go with 100 to start with and just see what happens. That might be too much or not enough, but it's just a guess. I think that's going to work. 50 probably would have been big enough there. And so I can see where they cross. How do I find an intersection on the calculators? Second trace, not value. Intersects, number 5. And then it's going to say first curve, you're going to hit enter. Second curve, enter. Guess, you can go over here close to where they cross if you want. And we get 37.68008. So T equals 37.68008 years since it happened. All right, and real fast, this last thing. 50 times 1.13 to the T power. If I am putting in the number of months instead of the number of years. Like, this is my equation for years. What would I have to do if I want to plug in like 60 months into this? Not 0.60. I divide it by 12, right? So this equation, if I divide that exponent by 12, that would make an equation where you can plug in months. All right. For this assignment, let's try, let's do the front page, number 1 and 2, okay? question on all of those. I read through them. I didn't work them all out. They looked okay, but if there's something you're running into, try something. We'll talk about them tomorrow. It's probably going to stay on Canvas. That whole thing is required because third period is going to have more time. You guys only have to do number 1 and 2, though. We'll get hopefully caught up all the way tomorrow.